Okay, let's talk about using the t-table. So the t-table works very differently from the z-table, okay? So you guys are used to looking up numbers in the z-table. The t-table is very different. So we're going to just cover using the t-table by itself first, and then we can incorporate it into problems, okay? So I'm not going to have any questions where it's just like, look up this number in the t-table, but that's what we're going to start off with now because this is a basic skill for the future problems. Okay, so you should have, all of you, a table that looks like this. This is a t-table, okay? So let me, let me move this over here. All right, so your t-table looks like this. And so let me just draw the picture of what's happening here, okay? The t distribution looks a lot like the normal distribution, but it's not the same, okay? You have something called degrees of freedom, which I'll explain in a little bit. But let's just say, for now, we will use this row with 5 degrees of freedom, okay? Do you guys see that? So on your table, find the row that says df equal to 5, okay? And what this says, the very first number that appears is 1.476, okay? 1.476. So your very first number that shows up in 5 degrees of freedom is 1.476. And the top of the column says t.100, okay? So t.1. Okay? And what this means is that if you have a t distribution with 5 degrees of freedom, and you draw a cutoff line at 1.476, you'll notice right over here it says the right tail probability. It says that this shaded area is exactly 0.100, or 10%. Is that clear? So 5 degrees of freedom, 1.476, the area in the right tail, or basically to the right of 1.476, is 0.100. Okay? So let's just check your understanding. If I don't draw a line at 1.476, but let's say I go further away, say I go out to 2.571, and I shade everything to the right in 2.571, how much is shaded? Shaded area is equal to 0.025, okay? Because t 2.571 is equal to t.025, so that means with 5 degrees of freedom, if I go further away to 2.571, the amount in my tail is now 0.025. Is that clear to everyone? No? Yes? No? Okay, so are you able to see these numbers that I'm referring to in this 5th row here, right here? Okay? So what I'm saying is, over here, 5 degrees of freedom, if I go 1.476, the area in the tail is 10%, 0.100. If I go further away from 0, 2.571, and I go to the top of the column, I have 0.025. Look at your reference table if you need to. The area in my tail is 0.025. Who's confused about this?
So wait, DF stands for degrees of freedom.
DF is degrees of freedom, yes. And I'll explain what that means in a moment. But just for now, I want to make sure we understand how this thing works, okay? So if our test statistic gets further and further away from 0, how much do we have in the tail? More or less? Less, okay? As we go farther away from 0, the amount that's left in the tail gets smaller and smaller, okay? Students always ask, why did that happen? But if you think about the picture, okay, as your test statistic gets farther from 0, the area left in the tail gets smaller, okay? So keep that in mind. As we go farther away from 0, the amount left in the tail gets smaller. Yes?
Is this only right tail?
This is the right tail. I'll talk about the left tail, which is the negative version, but I just want to cover this part first, okay? Okay, so quick check of your understanding. Let's say you have 17 degrees of freedom and t is equal to 2.567. How much is in the tail? Okay, so some of you guys shouted it out, but our answer is what? 0.01, okay? Yeah, just please don't say 0.010, that this is 0.01, okay? 0.010 is exactly the same as 0.01, but nobody says 0.010, okay? Because I could also do this. This is exactly the same value, and I would not say 0.010,000 or so. Okay, just say 0.01, okay? So 1%, okay? How much is in the tail? 1%, 0.01, okay? Is this good with everyone so far? So far, so good. Okay, let's try something else. Okay, let's say we have degrees of freedom equal to 5. Okay, and don't shout this out. Don't shout out your answer, but let's say the number I have is equal to 1.9. Okay, so I have 5 degrees of freedom, and our test statistic is equal to 1.9. How much is in the tail? Okay, so we're faced with a bit of a problem here. Okay, when we go to 5 degrees of freedom, I don't see 1.9 in there. Okay, what I do see is what? I see 1.476. Okay, 1.476 is closer to 0 than 1.9, and on the other side I see 2.015. Okay, and what the t-table tells me, actually let me use a different color, is that at 2.015, the area that I have in my tail is 5%, and yet at 1.476, the area I would have in my tail is equal to 10%. Okay, is that part clear to everyone? So if I'm drawing a line at 1.9, the area in my tail, I don't know exactly, is unknown, but I do know that it must be between 5% and 10%. Okay, it's between 0.05 and 0.1. And I want to make sure that's clear to everyone. Can we see that? Raise your hand if you can't see that. Okay, and so what I would say here is that my tail area is less than 10%, but greater than 0.05, 5%. Okay, because 1.9 is in between 1.476 and 2.015, so the corresponding tail area must be between 10% and 5%. Is that good? All right, so I'm going to just, and then, so let me just explain. If we had negative 1.9 instead, okay? The answer would also be exactly the same. If I shaded the area over here, my tail area here is less than 10% more than 5%, okay? And that's because the t-table is symmetric. So if you have positive numbers and you're looking for the tail area to the right, you use these. If you get a negative number and you're looking for the tail area to the left, you use the same exact numbers. Just ignore the negative sign. Is that okay? The table is symmetric, okay? So when we look up positive 1.9, when you have positive numbers, you can just go straight to the table. If you have a negative number, you can also go straight to the table. Just ignore the negative sign, look up the positive version, but just realize that instead of the right tail, you now have the left tail. Okay? It's exactly the same numbers, it's just now you're doing the negative side, and instead of the right tail, it's the left tail. Is that okay? All right, so let's just try a few drills. And don't shout out these answers. But I'm going to say, let's say you have degrees of freedom equal to 8, and your test statistic is equal to 2.5. How much is in the tail? Okay. And let's try another one. Degrees of freedom equal to 20. Okay, so you have 4 drills right there, so go ahead, find the answers to each of these.
Are you going to go over each problem?
Yeah, I guess so. But that doesn't mean you should just sit around and wait for me to come tell you what the answer is.
Of course not.
Of course not. How are we doing? Good. No?
Don't want to do it.
Are you trying?
I'm trying. Effort's always going to be there.
You know the right things to say. Okay, I'm going to just start putting up answers here. How do we do? Good? No good? Bad? Yes? No? Okay. All right. Yes?
I understood how you got tail is greater than 0.01 because I'm assuming you used 2.896 for on the chart.
What are you talking about?
The first column.
Okay.
So the part that says 0.01, I understand because you looked at the chart for 2.896 in the DF row A.
Uh-huh.
Oh, wait, no?
Yes?
Okay, yeah. So the part I don't understand is the 0.025. Were we supposed to pick the number closest but smaller than 2.5?
No. Okay. All right, so these are our answers. So the first one, our test statistic is 2.5, right? So let's go, we'll go to 8 degrees of freedom, okay? And we're trying to see where 2.5. So 2.5 is in between 2.3 and 2.896.
I need the 2.306 to 0.025.
2.5 is in between these two numbers. So my tail area is going to be in between these two numbers, 0.025 and 0.01. And that's what I have. 2.5 in that row is in between 2.306 and 2.896. So my corresponding tail area is in between there.
Thank you.
Okay? Is that okay? That one. 20 degrees of freedom. Okay, we're looking at 3.95. 3.95, 20 degrees of freedom. If I had to line it up, 3.95 goes out here. Okay? It's bigger than 3.552. So that means my tail area is what? More or less than 0.001? Less. What did I just say? The farther you're away from 0, how much happens to your tail? You get less in your tail. Okay? So we're farther away from 0 than 3.552. So the amount in my tail is less than 0.001. Don't mess that up. Huh? Farther away from 0 means less in the tail. Yes. Okay. Now I have negative 2.84 degrees of freedom. Okay. I just said ignore the negative sign. 2.8 is in between 2.776 and 3.747. So that means, or did I mess this up? Oh, I messed this up. I apologize. I read the wrong row. So my tail is greater than 0.01, but less than 0.025. Okay, I apologize for that mistake. 2.8. Okay. And lastly, test statistic, 4 degrees of freedom. I have negative 0.09, so I'm going to just look up positive 0.09. 0.09 is closer to 0 than 1.533, so that means my tail has to be more than 0.1. Is that okay? Okay. Occasionally, you'll be faced with a situation where your exact degrees of freedom is not found in the table. Okay. In those situations, you can we're just going to say always round down. Okay. So if you have 76 degrees of freedom, okay, you don't see 76 degrees of freedom, round down, and what do we use? Use 60 degrees of freedom, okay? Question?
Will the quiz be only chapter 8 or will this be covered as well?
It'll cover chapter 8 and 9.
Okay.
Okay? I told you what kind of question you can expect from chapter 8.
Okay. And this is the kind of question?
No, this is just one step of the types of questions we'll see in chapter 9, okay? But this is just one step that's important, and so I wanted to cover that clearly here, okay? So are we comfortable with looking up test statistics in the t-table?
Yes.
Comfortable is not the right word, but we can do it. That's fine. Okay. That's all I can ask for. Okay, so chapter 9 is all about hypothesis testing and confidence intervals for numeric variables. Okay. Chapter 8, what we did last week was hypothesis testing and mostly just hypothesis testing for categorical variables, okay? And we did confidence intervals the week before in chapter 7. Okay? So chapter 9 is all about hypothesis testing and confidence intervals for numeric variables, okay? And I'm just going to state we're going to have situations where we have one sample and we have situations where we have two samples. Okay? And you're going to have confidence intervals and test statistics, okay? So let me just put the ugly things up on the board now, okay? And get this out of the way just so we're not sad when we come and encounter them, okay? So the standard error for one sample is going to be S divided by the square root of n. So that's not too bad, okay? S is the standard deviation of the sample. And n is what? Sample size. Okay? And other things. Your sample mean is x bar. And your degrees of freedom is going to be n minus 1. Okay. So these are just, I don't know, put this somewhere so you can always refer back to it. These are going to be good to know, okay? When you have two samples, problems involving two samples, your standard error is going to be S1, because you've got the first sample squared divided by N1, and then you have the second sample, S2, the standard deviation of that, squared over N2, okay? So S1, standard deviation of sample 1. S2 is the standard deviation of sample 2. N1, size of sample 1. And N2, size of sample 2. Okay. You also have X bar 1, X bar 2. And your degrees of freedom is equal to N minus 1, but use the smaller n. Okay, so you've got two n's, right? You've got n1 and you have n2. Just use the smaller n for degrees of freedom n minus 1. Is that good? You guys copied that down? No? No, not quite? Okay, how about now? Yeah? All right. Okay. So we'll cover. There's going to be 4 scenarios that we will cover in chapter 9. Okay. Okay. We're going to have confidence interval for one sample. And remember, in chapter 9, we're always dealing with numeric variables. Okay. Confidence interval for one sample. Then we've got hypothesis test for one sample. Okay, again, numeric variable. Confidence interval for 2 samples. And then we also have a hypothesis test for 2 samples. Okay, and they're all numeric variables. We know the difference between a numeric variable and a categorical variable? Yes, right? So if I say we're dealing with people, we ask people, do you have a 401k account? And people say yes or no. Is their response numeric or categorical? Categorical, right? And so our summary data will say we asked 600 people, 350 of them have a 401k account or something. I don't know. I'm making that number up. Okay. Numeric variable, we might say we asked 40 people and we asked how tall they are. Okay. Numeric variable is height. All right, so anyway, we're going to cover each of these, but they're all very kind of similar. It's just going back to that page that we did here. Just remember, this is the stuff you have for one sample. This is the stuff you have for 2 samples. Okay? If you can keep track of whether you have 1 sample or 2 samples, you're in good shape. If you can keep track of whether you're doing confidence interval or hypothesis test, you're in good shape. Biggest problem or biggest mistake I see students make. They don't know whether they've got 1 sample or 2 samples. They don't know if they're doing a confidence interval or a hypothesis test. And then, they also get their chapter 8 stuff mixed up. They don't know if they're dealing with a numeric variable or a categorical variable. Okay? So whenever you encounter a problem, there's three things you must identify, okay? Identify categorical or numeric. One sample or two samples. And am I dealing with a confidence interval or hypothesis test? Okay. Keep track of these things, okay? If you can figure out this, well, you have to figure this out. When you read the problem, you've got to figure this out. This will set the pace on what you need to do and where you need to go, all right? If you make a mistake in this step of identifying what you're dealing with, everything you do is going to be wrong, okay? It's like buying the wrong map and hoping that's going to help you get around town. It's not going to work. You've got to figure this part out first, because this essentially determines which map you're using or what system you're going through. Okay, so let me just tell you the details for each part. Okay, today we're only dealing with numeric because in Chapter 8 and in Chapter 7 we dealt with the categorical stuff. All right, so let's start off with a confidence interval for one sample. Again, numeric variable. Everything we do today is dealing with numeric variables. Okay. The premise here, or the premise for any confidence interval, is that we want to make a statement about the population. Okay. We can't observe the population. We observe only a sample. Only a random sample. Okay. And so our sample, the information, the data that we have from our sample, we have the sample size n, we have the sample mean x bar, and the sample standard deviation s. Okay? And so from this, data, we make a confidence interval about the location, or about the value of the population mean mu. Okay, and we'd say, we are blank % confident that the population mean mu is between blank, that's an ampersand, and blank, okay? And so your high and low values are going to be x bar plus or minus t star times the standard error s over the square root of n. So it's very similar to confidence interval for from chapter 7 where we were dealing with a proportion. We had p hat plus or minus z star times the standard error. And now instead of p hat, we've got x bar. Instead of z, we have a t. And the formula for the standard error changed. Okay. It's like faces, all right? You look at one face and you look at another face. The eyes are different, the nose is different, the mouth is different, but it's still a face. You still have the same pieces, okay? Everybody's got eyes, everybody's got nose, everybody's got a mouth, okay? Almost all the time. Huh?
What's that little smidge in between the teeth?
Just a dot indicating multiplication. Okay? To indicate multiplication. So all of these things, you've got different, the things look different, the little individual pieces are different, but overall, we've got the same thing, okay? So let's do an example here, okay? So we have a random sample of, I don't know, random sample of mice. Okay? Now let's not do mice. I have no idea. Okay. Huh? All right, we'll do a random sample of German Shepherd puppies, okay? GSD puppies. Okay? German Shepherd dog, okay? And we will say there are 10 randomly selected puppies. Okay, so we're not taking puppies from the same litter or something like that, because that would not be random. The average weight of these 10 puppies is 11 pounds, or we'll say 11.3 pounds. And the standard deviation of these puppies is 2.1 pounds. Okay, let's say these are German Shepherd puppies. I don't know. I have no idea how old these are. 3 months old. Whatever. I'm just making something up here, okay? I don't know how big puppies are at 3 months. Maybe they're bigger or smaller, whatever. Okay, so we want to know, okay, based on this sample, what can we say about the mean weight of all German Shepherd puppies 3 months old? Okay, that's what we want to know. Okay, so we're going to make a confidence interval. Okay, let's make a 95% confidence interval. Okay, so from our data, we need to have n, x bar, and s. So what is n? 10, right? So when we read our problem, n is 10. X bar is 11.3. The average weight of our sample is 11.3. Standard deviation, 2.1. Okay. All right, so based on that, what is our degrees of freedom? Degrees of freedom, n minus 1, so we have 9 degrees of freedom. Okay? And the last thing we need to do is figure out T star. Okay, so T star, we're going to go to our table, and we have 9 degrees of freedom. And what is our confidence level? 95%. So what we do is we go to the top of the column that says 95%, and we go to the row that says 9 degrees of freedom, and what is the number that we see there? 2.262. So that's going to be our T star. Okay? So look in the table, 95% confidence, 9 degrees of freedom. And so now all we have to do is we put all of this together. X bar plus or minus T star times S over the square root of n. Okay, and so now it's just plugging this into your calculator, 11.3 plus or minus, and I'm going to do this work over here. 2.1 divided by the square root of 10, and I get 0.66407 or 408. So I have 2.262 times 0.6664. I'll say 0.6641. Okay, and I multiply that by 2.262, and I get 1.502. So I have 11.3 plus or minus 1.502. So let's do 11.3 plus that, and I get 12.802. And on the other side, I do 11.3 minus 1.502, and I get 7. I'm sorry, I messed something up. 11.3 minus 9.798. Okay. So my interpretation, perhaps the most important part, is I would say I am 95% confident that the mean weight of all German Shepherd puppies is between 9.798 and 12.802 pounds. Question? Yeah, the confidence level will be given to you in the problem, okay? And if a confidence level is not given, assume 95%, okay? Just like if the alpha is not given, assume alpha is 5%. If the confidence level is not given, assume 95%. But otherwise, the confidence level should always be given to you in the problem. Okay? All right, so based on this interval, someone asks, do we have evidence that the average weight is not 10 pounds? And what would you say?
No, because, couldn't you average the two numbers?
Well, the answer is no, because 10 is in between 9.798 and 12.802. On the other hand, someone says, do we have evidence that it's not 13 pounds? And you'd say yes, because 13 is not within your interval. Is that okay?
One quick question. How did you get the last
I did 11.3 plus 1.502 to get 12.802, and 11.3 minus 1.502 to get 9.798. Okay. So maybe I'll just put down, do we have evidence that the mean is not 10? And you'd say no, 10 is in the interval. Okay. On the other hand, I could say, do we have evidence that the mean is not 13? And you would say yes, 13 is not within the interval. Okay. You might see a question kind of like this on next week's quiz, okay? It won't be dealing with puppies, but I know, I'm sad about it too.